Okay. So, one of the things people don't oftentimes realize is that when they look at this table and they look at a micropipettes have a variable accuracy. Okay. And it depends on how much of the pipette amount you're using. In fact, it's kind of funny because, so right here we have the accuracy at 10% of pipette volume. Over here we have the accuracy at 100% pipette volume. Notice these are both in percentages, right? So if you use a 100 to 1000 microliter pipette, which is the bigger ones, the blue tips typically, if you do 100 milliliters, you're going to be 1.6 microliters plus or minus. Okay. If you do 1,000, on the other hand, you're only 3-ish. Okay. And so the percent actually goes down as you go to the higher region for the micropipette. It works better. Micropipettes do not work very well when you're delivering like 10%-ish. Now, an interesting little factoid is that a lot of places they'll use micropipettes and they'll do them out of range. And so they'll try to do like 80 microliters with a micropipette. What do you think happens to your accuracy if you do that? Yeah, it goes to hell really quick. Okay. And so also another thing to keep note, if you guys compared the accuracies on these tables to each other, in terms of percent accuracies, the micropipettes are actually really bad. Yeah. So if you actually compare in percent accuracy, the micropipettes are actually worse than volumetric pipettes. So they're not as accurate as everybody usually thinks. Okay, if you're doing high precision, high accuracy work, micropipettes are not actually the way to go every time. Okay, you may have noticed that the syringes are actually usually better accuracy. So those syringes you were seeing in there for like gas chromatography, all that, liquid chromatography, those are usually more accurate than a similar micropipette would be. And they're usually about the same price or less price. Okay, and more reliable. And don't get destroyed when you use organic solvents. So, like if you don't have to do a whole lot of different measurements very rapidly, usually you're better off with a syringe. And if you can just do a set amount every time, they make very specific transfer pipettes that are that amount. And those are better. Okay. If you do lots of different measurements over and over and over and over, micropipettes are kind of the best. They're fast if you have to change a lot. So, okay. Anybody want to change their answer? I'll allow to change the answer this time. Okay. Go ahead and change your answer if you'd like. Yes. You already did. Yeah. Okay. Anybody else want to change the answer? There's still one person that got it wrong. Okay. Feel free. Okay. Everybody got it right. Except for Will. No. It's okay. I missed way more classes than I probably meant to. Yeah. Yeah, I understand. It's okay. One of the reasons why I remembered to go ahead and let's go ahead and record. Yeah. Anyways, I honestly can't even like talk about it and be mad or anything, because I don't know if I've ever told you guys about when I took physical chemistry. I had to be warned that if I missed any more classes, I would miss more than 75% of the classes, and they could not pass me. Like of the entire semester. Yeah. And you can't actually get a grade and you automatically fail a class if you miss more than 30% actually at Cumberland. So 30% is the minimum number of classes you have to be at.
Is that like, and it's per class, not more?
Per class, yeah. Didn't know it, did you?
Well, for athletes, we have this thing where if you miss more than like 10 of your classes, then it's unexcused,
Mm-hmm.
and you have to like sit out games and everything. So
Yes.
they give, and
It's because you're starting to come somewhere close.
Oh, really?
Yeah, keep in mind there's about 30 classes in any given semester. So it's 15 weeks times 2, right? Yeah. Yeah, that's why. They don't want you to auto fail.
And they're strict with attendance at school because of like
Yeah, it is. Yep, you are exactly right. Yeah, we're under extra scrutiny that we have to fulfill.
Because at Lincoln Memorial, they did not care about attendance at all. So when I came here, I was like,
No, most universities don't care at all. APSU and us are very, very strict because we're both Tennessee's Promise. And we're probably the strictest 4 years I've ever heard of.
really?
Yeah. But yeah, it's because of the Tennessee Promise. Okay, so errors matter. This is actually an interesting example, but you know what? I'm going to use a different example for you because it'll be higher impact. Okay, most of you probably don't really care that much about Zika. Am I wrong? Anybody know anyone that's ever had Zika? Okay. So errors matter. COVID. Okay. COVID's actually an even worse example, right? So, does anybody know why everybody flagged false positives back during the initial COVID testings for like almost 2 years?
Not really.
Mm-hmm. Huh? The first slide in chapter 3. Yeah. Yep. So, yeah, I don't think there's actually anything I can like add to from those slides in the book on that chapter because it's kind of like just tables over and over and over. If you guys get confused about something, then please do ask me and talk to me, and I'll make like a video or whatever you guys need. But it would have just been me going to a table. See the table? See the table. And after doing that twice, I was like, you guys can. Okay. So what happened is there's a limit of detection on tests, right? And so you could detect a COVID virus being in someone from it having a single particle, and you just use PCR to replicate that over and over and be able to detect it. Okay. But do you catch a virus for having a single viron in your body? No. You don't catch a virus from having a single possibly damaged viron in your body. Okay. You need a minimum load of the virus. It's kind of like an invasion, right? If somebody tried to invade the United States of America right now and they sent 10 people, was that a serious invasion? No, it's not bringing down the USA, right? If they send 10 million people, is it a serious invasion? Anybody that said yes, you are conspiracy theorists, according to NBC. Okay, because 20 million people crossed the border illegally in violation of federal law over 4 years. But anyways, so sorry, I had to do that joke. For reference, I don't actually care either way that much. As long as they have a manageable route, I'm fine either way. But now, in the terms of COVID, what happened is they set that limit way too low. So you could have literally, they did cases where they only had 10 viron particles that they could detect, like full on. And they said those people had COVID. I forget the amount of blood sample they took, but per blood sample, it was in the hundreds. Yeah. So if you had, I think it was, if I remember correctly, it was 200 something, but it's been a couple of years since I actually looked. It was about 200 something particles per that blood sample. Yeah. And so when you're under that, your body is going to be able to successfully fight that off, even if you're immunocompromised. Yeah. And you can lower that for people that are heavily immunocompromised, but there's always a limit. Because viruses just do not like have intelligence, right? So they have to like bounce around and hit your cell in just the right way. And then they do work. And so they false flagged millions of people for having COVID. People got fired for not taking the vaccine because then they had COVID. People were had their clearances rejected. People were persecuted. People were not given loans. People were not given PPP where they would have normally qualified for it. So, like, people had their lives ruined over these things, and some scientist somewhere just completely screwed this up, right? Utterly. And that's not even close to like the end of the trail of stupidity that was our response to COVID. Okay. Not even remotely. Like scientists on all levels screwed up almost everywhere. Okay. It was really like the CDC and WHO proved themselves to be utterly incompetent, which was pretty bad. And there hasn't actually been that many changes that either. So we'll see if the next one turns out better, considering we didn't change anything from the previous one. Okay. Errors matter. Again, more than 13 billion clinical tests are going to be performed each year in the United States. Some results will be wrong. Improving reliability depends on the scientists' ability to recognize and prevent errors. You have to be able to make intelligent decisions. And at some point, you just have to accept that in a decrease in the uncertainty is not worth it. Okay? You're going to false flag things. You're going to mess things up. And at some point, it's just you will cause more damage by trying to be more certain. Okay? So this right here is the unacceptable errors per million lab tests. This is on a logarithmic scale. You will notice that these are getting better over time. A lot of that is actually computers right here. Okay? The introduction of computers. But again, better techniques over time. We lower those unacceptable errors that are happening from our lab tests. Okay. Now, let's talk a bit more about error uncertainty. So error is the difference between a measured value and the true value. Now, do you know the true value most of the time? No. When you're doing lab with me, yeah, you know the true value usually, right? Because I give you something that already has a value. But out in the world, you typically never know the true value. Now, there's always error that's associated with every measurement. There's no way of actually measuring the true value of anything at all. The agreement of measurements made by different methods is going to provide confidence that results are more accurate. So if you're not sure if you're measuring the true value using one method, what you typically want to do is ask another lab to measure it and ask for a different method to be used. This is one of the reasons why knowing these analog techniques that we're using here is actually important for a chemist. Like, yeah, the majority of you are probably going to go out and then you'll never ever use an analog method again. Okay? Like maybe you'll use pieces here and there, but almost all of them from now on are going to be instrument based in some way, right? Like at one part of that. But every now and then you'll run into a method where it doesn't have an instrument-based test yet. And every now and then you're going to run into one where something causes you to go, oh, this might be wrong. And then you have to fall back on another method to see if it agrees. Okay? Oftentimes in analog methods. Right, so uncertainty, this is the dispersion of measured values due to both random and systematic effects. So this right here is error because this is the true value versus the average measured values, right? But if we had taken these values here, we would have actually averaged to the true value, right? Okay. And again, that's that same thing that's accuracy versus uncertainty, right? Okay. Or accuracy versus precision, right? So these are just different ways of recording the same sort of concepts, okay? This is just the terminology from analytical chemistry. Again, these would be the uncertainty range that you would have here. typically these are going to be measured in amounts of standard deviations, and that's how you would report them. Normally you're seeing 1 or 2 standard deviations. Okay. Again, that's the width of the interval for the uncertainty. It tells you how uncertain it is. It also tells you what your last digit of certainty is going to be. Okay. Where your uncertainty is and your numbers. So fitness for purpose is incredibly important. This is something we've never really talked about before this. And this is where like actual real world chemistry comes into effect. Okay. So this is the degree to which the data produced by measurement enables a user to make correct decisions for the stated purpose. So can an analytical measurement answer the question that you've posed? Okay. Do you want everything to be absolutely an infinite amount of fitness for purpose? If you only need 1 decimal place, do you need to measure down to 10 decimal places? No. Fitness for purpose would tell you need to measure to the first or second decimal place. So you always get that 1 decimal place, right? And if you go past that, you've exceeded fitness for purpose, right? And at that point, any extra costs that are accrued are not worth it usually. Okay. So significant figures, you all probably remember this from Gen Chem, hopefully, ish. Sig figs. Yeah, kind of. Okay. A little bit of review. So significant figures, these are going to be the minimum number of digits that's needed to give a value in scientific notation without a loss of precision. Okay. Significant figures typically indicate the last digit where you have your uncertainty is located. Okay. So this number right here has 3 significant figures. That is 1, 2, 3 significant figures. All right. Zeros are where you're going to run into a little bit of troubles for sig figs. Okay. Anything that's non-zero is a significant figure. So right here we have 3 significant figures. Here we have 4. Notice that this has a decimal place. Anything to the right of a significant figure when you have a decimal place is going to be significant. Okay. So see how that 0 is to the right? It's significant now. And zeros that are not significant are called placeholder zeros. Okay. There are zeros that have to be there due to the fact that you can't write the number without them. Okay. If you write scientific notation properly, by the way, you're always going to have significant figures, and that's it. You'll never have to deal with non-significant figures if you write it properly. Okay. Now, again, this would be another 5 significant figures in this case. See, these zeros are significant. What those are telling you is that first one right there, 9.25. That 5, I am uncertain about. I have some degree of uncertainty about that 5. Okay? That's where my balance is bobbing around, and I'm not sure about that number. Okay? That's where I've had to estimate between the lines on my analog measurement, right? So that 5, it could be 4 or 5 instead, okay? I've rounded it to 5. I'm not sure if it's actually 5, okay? Okay, that 0.250, what does that tell you? By the way, this is something really common for physicists to mess up on. Huh? The 0 is where I rounded, or another way of saying that is the 0 is where I have my uncertainty, right? This is very common for very smart people to mess up on, by the way. They will like give you a number that's like that, the 5 significant figures, and then you find out the technique they use to measure it is only significant down to the 0.2. I'm not joking. I once, so have you guys ever heard the words Peter growing around my mouth? Yeah. Okay, some of you have, some of you haven't. Probably the smartest person I've ever actually met in person. He's the guy that like Jet Propulsion Lab, which is the experimental smart people NASA, ask questions to. And are like, you need to come down because we have these projects and we can't figure them out. Okay? Just brilliant. Absolutely brilliant. incredible mathematician, incredible computer programmer, really crazy good. Uh, we once gave him a microwave Spectra we were trying to fit, and we're like, this is taking a really long time. It's been 6 months. We usually fit them ourselves in like maybe a week. Okay. Like you can do them in a week. If you're like spending an hour or two a day, maybe it takes you 2 or 3 weeks, but 6 months is ridiculous. And so I go up there. I'm talking to Peter Groner, really actually a sweet guy, really nice guy. Awesome to meet, actually. I don't know if he still goes to conferences, but if you ever get a chance, great guy to meet. You'll have to wait in line because there'll be like 100 scientists all following him around trying to get him to solve things for him. But so we went up to him and like, what's going on? Why is this taking so long? So he shows me the work because he likes talking about his work. And he goes, I'm trying to fit this out. He's trying to fit the 10th decimal place. The error on the instrument is in the 4th decimal place. He's 6 decimal places down from where the uncertainty is and trying to get that perfect. And I'm just like, can I have that? Okay, so just so we're clear, there's no meaning to this extra decimal places. And he's like, I think he still worked on it a little bit after that. But he was mildly on the spectrum. One of the people I don't like to be touched on the spectrum. Yeah. But so I think he did actually fit the next one. But like, God, I hope he found something else to do after that. I know he did other projects after that, so must have. Anyways, so this one right here, these right here are placeholder zeros. Everybody see those okay? Okay, and so the decimal place is right here. So we skip these zeros in terms of significant figures, and these are the first significant figures. So that's 3 significant figures. Okay. Okay. Have you guys ever heard of the Superman virus is what people usually call it? Also, The Office. You ever seen that movie? No? That's sad. Both are kind of sad. They're both good movies. So it's actually a virus that hackers have used. I know I have 5 times they've used it, but probably there's more times. And what they do is they infect bank computers or very large systems. And they take and have, so like, let's say this is a dollar amount. They did an interest calculation on your savings account. Okay. And you should have gotten paid 2.599. Okay. What the bank does is it actually chops off at one point and then rounds. Okay. And the bank keeps that extra fractions of pennies that you never see. What the virus does, it goes a couple decimal places down, chops those off, and puts that in account. Now, it doesn't sound impressive. You're taking like 1,000th of a penny, right? Maybe 10,000th of a penny. But it is really impressive because if you go to a large bank and infect their system, they do millions of calculations a day, right? You literally could be talking about tens of millions of calculations a day for even a like citywide bank. Forget something like Chase, right? Which Chase has been infected, in fact, in California. Yeah, the Chase branches in California. And so these things, they get away with like $600 million over the course of 3 years. Was the last one I know of is a Ukrainian group that did it about 7-8 years ago, I think. I think they actually got away with it. I don't know if they ever actually, I know they caught one of them for an unrelated thing. I don't know if they ever got the money back though. Yeah. So that one was. Anyways, people have been doing that since like the 1980s. Yeah. ATMs. Okay, so there are uncertainty in measured quantities again, and any measured quantity, there is uncertainty into it. Without the uncertainty, really the measured quantity is not meaningful because you don't know what actually you're measuring. It'd be like me saying, yeah, I really measured out that dose that you're going to take really well. And what if you don't know the uncertainty? Do you want to take that dose? What if I just took this and I went splash? Do you want to take that dose anymore? No, you could be like plus or minus 50%, right? Yeah, you'd be in a lot of trouble. Okay, so whenever you're reading the scale on any apparatus, the estimate is all readings to the nearest tenth of a distance between the scale divisions. This is called interpolation, and it's what you have to do anytime you're using an analog scale. Okay, so like if you're using a ruler or a burette or any of those things, graduated cylinders, you always are going to measure down to a tenth. Now, the tenth is going to be very difficult for you to actually interpolate and figure out. Typically, most people say that you're probably about the fifths is probably pretty well. You probably did a good job there. The tenths, you probably didn't do a great job. Okay. But the tenths is the next digit down, right? Okay. Now, significant figures in arithmetic. This is where we're getting into new things. Okay. Or we're starting to see the new things come. So within calculations, if you multiply and divide, you need to use significant figures. If you add and subtract, you need to use the least number of decimal places. Okay? Anybody know why that would be? Let's say we have a number that I'm going to apply to your bank account, okay? So I'm going to subtract 0.0001 pennies. Okay? Are you going to be mad at me? Not really, right? Probably don't care. Bank does it to you all the time. Okay? And so if I add or subtract a very small number, it doesn't actually change anything, does it? I just round right back up to that other number, don't I? But what if I multiplied your bank account by 0.0001? Are you going to be mad at me? Yes, you're going to be really mad at me, right? Because your bank account just went to almost zero, right? Yeah. So notice again, that was one sig fig, right? So that wasn't a lot of change, was it? Well, with multiplication division, that's a huge amount of change. Now, if I divided your bank account by that, you'd be really happy. Life would be good. Right. Now, spreadsheets typically will retain all the digits whenever you do calculations. They actually do max out, but it's something ridiculous like 20 digits or 30 digits. I forget which one they max out on. I'd have to look that up. But the digits they show you on the surface, though, will round based on the formatting you have. Okay? Whenever you do calculations, you should always try to not round as much as possible. Right? Okay, so this is some different examples. These are multiplications. So when you do a multiplication, what you should see is when you, I'm sorry, these are additions. Didn't look apparently, or didn't comprehend what I was looking at. So when you do an addition or subtraction, what you need to do here is you need to put all of these numbers in the same number of decimal places. Okay? So notice, for example, this is 10 to the 5, 10 to the 3rd, 10 to the 6, right? So choose one of these, rewrite them all so that they're in the same 10s to the 5 in this case. Okay? Did you have to do 10s to the 5? No. You could have done whatever. Okay? 10 to the 3rd would have been fine too. Okay. So the next thing you're going to do here, usually it's easier to do the largest one, but in this case, we were only one across and this 0.9. So this one's actually the easiest one to look at. Okay, so once I'm in the same scientific notation 10 to the power of, okay, I'm going to line all of my decimal places up. And the one that has the least number of decimal places, that is where my sig figs end. Okay? Because, like, for example, anything lower number of, with more decimal places, like subtracting this off of this number, what would you do once you subtract that? Well, it'd go to 993, right? And then you'd round it right back up, wouldn't you? And it wouldn't make any difference. Can everybody see that okay? So like that 7 right there, that doesn't matter at all, does it? You're just going to round it right back away. Okay.
Is the 0.984, is that 4 sig figs with the 0 in front?
This one right here?
Sorry, no, the 10 to the 6, the 0.984 on the furthermost left.
Oh, this one?
Yeah.
Oh, that's 3.
Okay, so
Yeah. So this one's not significant because you haven't hit a significant figure yet.
Okay.
Yeah. So decimal places, you start over here, trace over until you hit a significant figure. And then the zeros start becoming significant. That make
Yeah.
Okay. Everybody got that okay? Okay. You're going to do essentially the same thing with subtractions.
Mm-hmm. Shouldn't our answer only be 3 sig figs then instead of 4?
Don't worry about sig figs. So when you do addition subtractions, I personally wouldn't even recommend counting sig figs.
Okay.
Just completely ignore it. Just operate on decimal places. Okay? Because when you do addition subtractions, your number of significant figures, sig figs, can actually change. So think of it like this. We actually have this case happening here, right? This is 9.84. We got that up into the tens place now because we added to it. And so that actually did increase the number of significant figures. And you can think of it a bit like counting. Like if you sit there counting out money, right? You can count the dollars usually. You usually get that right. But typically people mess up on the change, don't they? Yeah. And so your uncertainty would be in the change. And like just because you added 1 plus 9 doesn't mean all of a sudden you would be, I don't know if I have 50 cents or 90 cents now. Right? Like that's not where your problems are going to be. That making sense?
Yeah.
So whenever you add and subtract, don't even bother with sig figs, just decimal places, okay? Do you see how this is subscript? What is that saying to you?
That it's past the last decimal.
Yep. Those are uncertain or those are not significant figures, right? And this is actually the way most, like a lot of journals and stuff will do that if they want to show you the next numbers, okay? So like you have a limit to your certainty, but those numbers pass, like oftentimes your numbers for your uncertainty are going to be conservative in science, okay? And they're going to be bigger than they actually might be in reality, okay? Especially on things like instrumental methods where you could be much more certain than you think you are, but you have other places where you're not sure about, okay? And so this is telling you, yeah, these are those numbers if you ever want them. Okay. Okay. Anybody have any questions so far? All right. Anything get confused here? Okay. You see the line there? So this is usually the easiest way to do it. Just line up the decimal for all of them. Make sure your times tens are the same if you have times tens. And then literally just draw a line through and chop. Add everything up with your calculator, and that's where you're going to round. Okay? If you're writing it out like this, you don't have to round. So, does anybody know the rules for rounding? Okay. What would I do for rounding for that? Yeah, so that's 1 here, right? What would I do for that one? Round up. What if it's 5 right there? Who's up? Who's down? Yeah, the one you learned in middle school is probably wrong. Yeah. Yes. So 5 is not the halfway point, is it? So 5, 1 through 5, has the same number of digits as 6 through 10, isn't it? So the half point is actually 5.5, isn't it? Because it's not an odd number. And so what happens is if you round, did you say down or up? For 5? Okay. So depends on the book, you see. Like I have a textbook that I teach in for the 103 that also does this wrong and gives the wrong rule. And it's basically any like 100 not science major class, you'll see that rule pop up. Yeah. High school, middle school, it doesn't matter. They do that all the time. So what will happen is if you round that up every time, you'll end up accumulating errors upwards every time. And so if you do that over and over and over, let's say you're doing a spreadsheet, you do it 100 times.
So you should just do 6
Wouldn't it
now.
be? Wouldn't it be 0 to 4, 5 to 9?
It's the same way. So if you're 5 to 9, then you're actually going to end up with too low of a number if you do it every time. Now, there's a few ways to do this to get the right answers overall. Okay. Now, keep in mind again, all you can really do for this rounding is try to keep it from accumulating errors. Okay. Okay. So what you want to do is the rule typically that most people follow is they just make everything for the next number evens. Okay. And so anytime it's odd, you round up. Anytime it's an even beforehand, you round down. And that kind of keeps you half and half. Because that's what you actually want to do. You want to round down half time, up half time. Okay? And so that's the rule a lot of people use. The other way this works is if the next number is above 5, you round up. The next number is below 5, you round down. Okay? And that will, again, eliminate most of that error. Because you round up half the time, you round down half the time. There you go. Okay? Okay. Is that making sense? Okay. It's a little bit more complicated, which is why in middle school and high school, they just don't. 5 up, right? Yeah, I always forget which way they do it, though. And I think there's books that do it the other way. I swear I've seen it the other way, too.
I think what he said is like how we've been taught this for us. It's just 0 to 4 is not, and then 5 and up.
Yeah, which is wrong. Yeah, I know, right? Yeah, math people, they don't know anything about error at all. Yeah. They always think there's no error. Hell, math people think 3.99999 repeating is 4. They even have a whole proof. So, I don't know, people. There's things that is good about math, but sometimes you gotta wonder they're playing in their own heads. Okay. So notice again that adding can actually cause your number of significant figures to go up, right? When you subtract, you can cause your significant figures to go down, right? What if I took the numbers 1.000 and 1.001 and took the difference between those? Whoa. Look what happened to my sig figs. Damn, right? Yeah, I just got rid of almost all of them. So keep that in mind. That addition subtractions, you can change your number of sig figs. Okay? In fact, it is very, very likely you'll change numbers of sig figs. Okay? It's kind of a coincidence if you don't. All right. Does anybody have any questions about that? Okay. So multiplication division. This is where you use sig figs, because if I multiply something by a number like this, like that's not going to change the accuracy of that. Okay? You can kind of think of it like this. It doesn't matter how many times I multiply it by. It is just going to scale all of the things about it, right? Including the uncertainty with it. Okay? So for example, on these cases right here, we look at these two number sets and we just count the number of significant figures, 3 for each. And that's the number of sig figs down here, right? We look over here, and what we need to do is we need to count the least number of significant figures, okay? Do you have to count out the ones with more sig figs? No. You're going to always take the number with the least sig figs. So for example, here, I see this one has less sig figs, so I count 2 sig figs, and that's the number of significant figures for my answer, okay? Does everybody understand why that is and how that works? Did I lose anybody at all? Okay. Doesn't matter whether it's division or subtraction, or division or multiplication. It's the same thing. It's still those sig figs, okay? The least number of significant figures. So just count the least number of significant figures in your problem, and you're good to go there. Okay. Okay, now logarithms. This is where you probably have actually never seen this rule. Did anybody see sig figs for logarithms? No? Ooh, Okay, new stuff. Now, the logarithm of n means that n equals 10 to some power, right? Okay. So the log of n equals a. Okay? The other way of thinking about this is when you take the log of a number, what happens is you're actually going to move this power out in front of that log, right? Okay. And so what ends up happening is the logarithm is composed of a characteristic and a mantissa. Okay, these are what these two parts are called. All right. So the characteristic is the integer portion. It's in the front. Okay? And that is not actually an uncertain number. There's no uncertainty to that because that's the numbers of tens. All right? The mantissa, on the other hand, is the decimal portion here. Okay? That's where your uncertainty is going to start kicking in. Okay. So, for example, if we take the log of this number here, we have 2, which is the characteristic. And then these decimal places right here, this is the mantissa. Is everybody okay with that so far? Huh? Yes, it would have been in the adaptive learning. And in the it'll be in the post as well for this chapter. Okay. And so the number of digits in the mantissa is the log x equals the number of significant figures in the x of the thing inside the log. So for example, if you take the log of this number here that has 4 sig figs, the mantissa is going to have 4 digits. And that's the number of significant figures in it. Okay. The reverse is also true. If you had like a value in here that you're trying to figure out the number of significant figures for, you're doing the anti-log, it's going to be the exact opposite. Okay, let's look at an anti-log problem real quick. Did everybody get that one though? So you take a log of something, the number of significant figures becomes the number of decimal places that you put. Okay. Positive, negative, doesn't matter. This number here, this could be 7, this could be 10, this could be a million, I don't care. Doesn't matter. Okay? That not for sig figs. This is the only part that you apply your sig figs to, your decimal place. Okay, so let's talk about doing it the other way. So the logarithm of n, this is that logarithm of n again, right? And we can actually take the anti-log instead. So what is an anti-log? It's not just that button on your calculator, right? It's 10 to the power of. Okay? So if you're on doing a log, you take 10 to the power of, right? And that comes from this same formula. Remember that? This was that definition right there. Okay. Okay. And so the number of digits in an anti-log of x is going to be the number of significant figures and the mantissa of x. Okay, so if we take the anti-log of something, we're going to look at that mantissa. That's the decimal places, right? That's our number of significant figures. I don't care what this number out here is in the whole number, the integer numbers. Doesn't matter. That's not part of our significant figures. Okay? It's only the decimal places that we're going to take. And that's going to be the total number of significant figures of our answer for an anti-log. Making sense? Notice they're just the exact opposite of each other. Okay. This is stuff that you'll pick it up more as you use it. Again, we're partially learning language and math, of course, both for heavily practice-based. So, types of error. Every measurement has uncertainty. Keep that in mind. Every single measurement, no matter what you do, has uncertainty. I don't care if the fancy computer tells you have 1,000,000 digits. It has an uncertainty, and it may not be 1,000,000 digits. Make sure you read the manual. Has uncertainty. The experimental error is going to be the difference between the true value and the measured value of a quantity. There are 3 types of experimental error that we have to discuss. There is systematic, there's random, and then there is gross error, is what you typically want to call it. But it is blunder. It means you or whoever did it screwed up. Okay? You messed up and whoops. Okay? This also is sometimes just called whoopsie if you want to be funny, but usually it's not funny. So when you're talking to somebody else and you don't want to be sounding stupid, you call it gross error. Okay? When you're joking around with your own other guys, blunder, or gals, whoever's around you. So systematic error. These are actually the ones that are most correctable, but the hardest to find oftentimes. So systematic error or determinant error, because it's always going to affect things the same way. Okay? So it's predetermined error. This arises from a flaw in equipment or experimental design. Okay? So let's say, everybody's used tape measures and rulers, right? Okay. Let's say I have a really old ruler and I've cut a part of the front off of it. What's going to happen to all my measurements? They're all going to be short, right? Every single one short. Okay? And so that would be systematic error, wouldn't it? Yeah. Did any of you do like a calorimetry experiment back in Gen Chem where you used like a thermometer? Did you calibrate the thermometer? Damn it. Okay, so typically you need to calibrate thermometers because they have systematic error, which is that there's always a little bit that's either too much or too little of the fluid inside. And so they'll always measure like a degree off. The alcohol thermometers are usually about 1 to 3 degrees off. So they're actually pretty bad. So if an experiment is conducted again in the same manner, your error is going to be reproducible. The measurement results are going to have consistent positive or negative bias. They can be percent bias or they can be pure bias, where it's just like +1, +3. But they can also be a percent bias. Depends on the measurements you're using. Or logarithmic scales. These can be discovered and corrected in theory. Okay? They're actually pretty difficult to discover and correct because you typically only have like one instrument for most labs. Now, if you have lots of instruments and you have a variety of instruments that you can use against each other, they're easier to find. Okay? Usually to find these, you actually have to take and get other labs to do testing on the same materials and then other methods to be used. And that's usually how you find systematic errors. Now, the nice thing about systematic errors, they're always scalable and reproducible. So if you have a systematic error, you can oftentimes just correct it by doing a scaling factor. Okay? That's how most businesses and labs correct them. So let's talk about detecting this. So what are some ways to detect systematic errors? You can analyze a known sample. This is actually a common practice in industry and the scientific field in general. That's what certifications are for, by the way. If anybody's ever noticed certification, like there's a little sticker on a lot of instruments that's certified and that gives a date. Okay. Have you guys used the micropipettes? The micropipettes have them on them, or they have them in the box. The analytical balance has it on it if you look at that. Okay. You can use a different method to measure the same quantity if the results do not agree with an estimate random error. There's a systematic error in one or both methods. You can participate in an interlaboratory comparison where different labs will analyze identical samples by the same or different methods, and that will give you a very good idea if they're systematic or random errors and how much each is if you do this often enough. You can analyze a blank sample. If you observe non-zero results, your method probably has a systematic error. And that's one of the reasons why when you do a calibration curve, you never set it to 0, is because you actually want to know if you're positive at the y-intercept or negative. It tells you if you have systematic errors. Okay. Some of the ways to minimize systematic error: calibrate your instruments. For high accuracy work, you have to calibrate your glassware. To optimize sample pre-treatment procedures to minimize analyte loss. So your treatment procedures are very, very common source of systematic errors because of your lab practices. Your standard additions can really help, or internal standards. What these can do is they can correct for matrix effects. Matrix is everything around an analyte you're measuring, right? So if you add spikes of known quantities to a sample, then you know you need to have that amount plus whatever, right? And so you can tell if you don't have that amount, then you have problems, right? Okay. And it actually does a very good job of sussing out where you have bad lab practices, by the way. By the way, in industry, they typically have somebody that will just do that. So they'll take samples, they'll set some in your rotations, and they'll have standard additions to them. And then they'll be able to look at your data and go, bad practices. These are batches, probably not good. Okay? And then you guys can rerun. Measurement bias. So measurement biased estimate of systematic error. It's going to characterize the trueness of the measurement. So right here, this would be a measurement bias, okay? And so right here, we have the true value. We're biased upwards from that true value by approximately that amount right there. That would be like that tape measure or ruler example I gave you, right? In this case, we maybe our tape measure, we've taken that little tip and we've expanded it over. And so now we measure long every time, okay? Okay, so random error or indeterminate error. These are going to be randomized, okay? You can't actually get rid of all random error, but you can reduce it. This arises from uncontrolled variables in the measurement. Literally in Raman spectroscopy, this used to be really funny because we take spectra and we get these lines in our spectra, really sharp, really big lines, and they're literally cosmic particles from outer space hitting our samples. And so we just cosmic particle, bam. Totally uncontrollable, nothing we can do. We could be in the middle of the planet and it still will not block all that. Okay. And so that's a source of random error, right? Now, this always has an equal chance of being positive or negative. And so if you do this enough times, guess what's going to happen? What if you just added every time you did a problem, you just add one, then subtract one? Would you get the right numbers at the end? Yeah. Yeah, if you just add one, subtract one at the end all of your time, you're going to get the right number because you'll just undo everything you did, right? So random errors are like that. If you do enough tests, you'll actually cancel out your random errors, okay? And so this is why we do that plus minus value, and then we report the average value in the center as the true value. We're assuming those standard deviations, the plus minus values, we're assuming those are random error, okay? And so they should cancel out, and we should get something within that range, okay? Mm-hmm.
I think I understand the difference between this one and systematic error, but with this example, electrical noise in an instrument, why wouldn't that be a systematic error when it's a flaw?
Because it's random. So what happens is, okay, so let's use the lights as an example, right? Tennessee has a tendency, we don't have like a super interconnected grid. So we experience, actually, we have a pretty interconnected one here. Does this happen where the lights flicker and they go brighter, dimmer sometimes? You guys know what I'm talking about? Okay. Yeah, our grid here is pretty interconnected, so I'm not sure if that happens a lot here. But like places in Tennessee, it happens a whole lot, right? The reason that happens is how electricity works. So the voltage on the line in your house is 120 volts nominal. In reality, it's actually 110 to 130. And it literally just varies completely randomly. Okay? Theoretically. Okay, so what will end up happening? Let's see you have a source of light. Okay, and you're measuring how much light passes to the other side. The voltage spikes up to 130, you're going to get brighter light, right? It goes down to 110, you're going to get dimmer light. And that's going to happen literally millions of times a second. Because that voltage actually has a frequency. It actually happens 59 times a second, actually. Has a wave. Yeah. But, so what you're actually seeing is you take multiple spectra when you do a spectrum, usually something like 50, 128, something like that. And then what you do is those all get added together. And if you watch the spectrum get taken, what will actually happen, it's kind of interesting and fun to watch, is you'll actually see something that looks like this. And then the next one, like out of phase. And that's the electricity. In phase, out of phase, different times, and you're getting variance in the voltage. That's then translating to brightness and dimming. Now, if you average all of that, you just get a line, right?
Yeah.
And it all cancels out.
Okay.
And that's random error. And electricity in like digital instruments is probably the single largest source of random error.
So is the difference between these two is with like random error, it's not really something you can control?
Uh-huh.
Okay.
You can do things to try to limit random error, but it is the most important thing is its randomness or indeterminate. That like it's not always going to be high, it's not always going to be low. Is that making sense?
Could it also be like it's not always going to happen, but maybe in a different trial it could happen? Or...
I mean, most random errors, yes, that is true. They're not going to happen in every single trial. But it's more the outcome that's important. Because if you have something that doesn't happen in every trial, but it's high, that would be a systematic error. And in fact, that's very common in labs. Or that you'll have a systematic error that is a bad employee. No, like you're like, yeah. Like, it's fun. It's actually kind of fun having somebody in the class that like is in a lab currently, because most of you are like, really? People are not going to be incompetent.
There's one.
Yes, there's always one. And they will literally be a systematic error for that lab. And it will not always be every experiment, right? Because they'll not be assigned to every experiment. And it could be an intake person. It could be a lab tech. It could be the boss of the lab. I know one lab had troubles with a systematic error. They could not figure out what the hell it was. And we talked to the lab, and literally what it was is like the person in charge and head of things would come and like talk to his employees about what they're supposed to get done and do things and try to make changes. And the person won't be able to pay attention to what they're doing. And they'd like put wrong droplet sizes. And they'd screw up. And so it was literally the boss coming in and watching you. And you guys will experience that in the labs here. You'll notice that whenever I come up and like watch you do stuff, you'll start screwing up more. And yeah. So I will literally be to you guys a systematic error that is inconsistent. And the random error will be things like the pipette doesn't always deliver the exact same amount of stuff. The electricity on the balance causes the measurement to change a little. Yeah. Does that make sense?
Yeah.
Okay, definitely. Now, subjective reading of scales, if you take enough people doing it, it will be a random error. If it's always you doing it, and it's always like two people doing it, it'll end up being a systematic error. Okay? Have you guys ever heard of wisdom of the crowd? No? So if you get a bunch of people and they don't communicate and they all make predictions, they'll be like scary accurate. So they'll look at a jar of jelly beans with 1,000,000 jelly beans or something in it. And if you just get random, like 10,000 people to guess how many are in there, and they don't talk to each other at all, they don't communicate to each other, they'll guess it almost to the jelly bean. Okay? But if you let them talk to each other, one of them will convince the others and they'll get way off. Yeah. So people get that wrong all the time. They don't do the second part that I just talked about. Yeah. And then it doesn't work. Yeah. So blunder or gross error, this is due to accidental but significant departures from the procedure. Now notice that if it follows the procedure and it is a stupid procedure and is wrong, that is still what? Systematic error, because it's the procedure, right? And so the procedure will always be wrong in the same way if you follow it, right? Okay. Blunder is where you're diverging from the procedure. Okay. By the way, always call it gross error if it's you. Okay. That's career advice. Okay. It is always, guys, ready? I made a gross error. Everybody with me? I made a gross error. Yeah. What do you not say? The blunder. Okay. Okay. There we go. I've saved your job. You will eventually make a gross error, and it will eventually become a thing. So this is going to be caused by procedural, instrumental, or clerical mistake. It's going to be unrecoverable. They should be recorded in your lab notebook so you know that they happened. Again, it's a significant departure from the procedure that you actually notice. Sometimes you make these and you don't notice. Maybe so serious that the data is rejected or experiment is redone. Not uncommon. It could be calculation errors, overshooting titration endpoints, dropping, discarding, contaminating a sample. Very, very common one right here. If you do those, please note it in your book, your lab notes. Make sure the person that's above you knows, because very likely this can't be fixed. Okay. Instrumental failure is another big one. This is the one gross errors that's not actually you. This happens quite a bit. Instruments do go out. So the certified reference materials, these are national standard laboratories, distribute them, and it's called a certified reference material. And you can get various different certified reference materials. You can get everything from peanut butter to chocolate to different antibiotics, whatever. Okay. The important thing about them is they're going to be certified reference. They make big batches. They store it very carefully. Then they measure it constantly and make sure it matches up when they send it to you. Okay. And so everybody will be the same. And so they do that for drugs. They do that typically, the NIST does this, which is the National Institute of Standards and Technology. They're actually a semi-coalition government outfit. Okay. And so it's kind of interesting because they get a bunch of labs that help them out, and then they get money from those, and they charge you like $10,000 for a little thing of peanut butter. I'm not joking. Okay. But they send you certified reference materials, and then that allows you to detect any errors if you run those. So let's talk about some students analyzing a series of unknown samples using proven titration procedures. What could go wrong here, right? And so we look here. These are all the percent of identified errors that we see from all these students. And for example, calculation is typically the most common error that you see from a student. Here we have procedure error. They messed up the procedure, obviously. Whoopsie. gross error. Poor precision, they don't catch that last little digit, right? They don't measure properly. Outliers that are not rejected, then we have reporting error, graphing error, significant figures, dilution factor, etc. Okay? All right, so obviously about 85% of these failed experiments are actually due to blunders, gross error, right? So precision, this describes the reproducibility of a result. You measure several times, and then the values have to agree. You need at least 3 measurements to actually perceive precision to some degree. The measures several times, and the values vary widely. These are not precise. Trueness, this is going to be how close to the average value is to the true value. If the precision is perfect or an infinite number of replicates have been performed, you do enough replication, your on precise data will eventually sort of work itself around. So the accuracy, this is going to describe how close, unless it's systematic error, by the way. If you do systematic errors, it doesn't matter how many times you do it. You're always going to be off. Okay. Accuracy, this is going to describe how close a measured value is from a limited number of replicates to the known or true value. Everybody see the difference between these? Okay. Accuracy, you have a limited number. So real world, right? Trueness is going to be when you have an infinite number. Okay. So not real world, right? You can never actually get trueness. You can approach it. Okay. Okay, so a measurement might be reproducible, but may be wrong. In fact, that's fairly common. Okay? In fact, most of our constants are probably reproducible, but wrong. A little bit, not a lot. Hopefully within the error. Okay, so absolute versus relative uncertainty. We've been talking about uncertainty, and we have like these percentages, and sometimes it's not a percentage, right? Okay. So absolute uncertainty, this is going to express the margin of uncertainty with the units of the associated with any measurement, and it's going to be in absolute values. It'll have plus and minus. It won't have a percentage. It will be in those units. Okay? And so this right here is an absolute uncertainty. So literally this value here could be 7 or it could be 3, right? And that would be our range that our measurement should fall within. Okay, so relative uncertainty, these are going to be percents, okay? And they're going to compare the size of the absolute uncertainty with the size of its associated measurement. You take the absolute uncertainty, you divide it by the magnitude of the measurement, and then you do times 100% to make a percentage, okay? And so we see here, this is the absolute there that we got up here. We divide it by the measurement, the average value right there. That's going to give us our relative uncertainty. Then if we want a percent, it's going to be percent relative uncertainty. We take the relative uncertainty times 100%, and that will give us our percent uncertainty. Okay. Oftentimes shortened to percent uncertainty because percent automatically means relative. So, okay. This is how you propagate error. This is one of those things that you're going to want to practice, and we're going to have to see where you guys have this go wrong. Okay. There's a few different formulas you'll have to use in this. They're all in the book, but also in here. So most experiments are going to require arithmetic operations. You have these errors that we've been talking about just now, these absolute and percent errors, right? Relative errors. Okay. So these uncertainties of the final result is not simply going to be a sum of those individual errors. The random error means that the random error is positive and some negative. There will be cancellation of error due to these errors being positive and negative. And so you don't just add together random error and it just compounds. They actually do cancel each other out, okay, to some degree. So there's several different propagation of error equations that you need to see. This one is addition and subtraction. This is going to be the absolute uncertainty right here. See how it's the U with no percent? Okay. Okay. This is multiplication division. It's going to use percent relative uncertainty. So this one's a percent relative uncertainty. See how it's a percentage right there? Okay. Okay. See, this is U1, U2. These U's are uncertainty. You know, probably got that from that. This is the first, second, third measurement. Then your value for that percent on that absolute uncertainty, excuse me, is right here. Okay. Notice that these are squares, and then you take the square root of those. Okay. Okay. Now, mixed operations, these are going to follow the proper algebraic rules for mathematical manipulation. So let's go ahead and see this in actual effect. So right here, we had your addition subtractions right there. So we're going to use this formula here. Okay. Okay. Right here are errors for each of those. This is going to be the error we're going to get for that number. That'll be U4 here. Okay, so we take these errors, we plug that in here, we square. We take this error, we plug it in here, we square. We take that one in here. If you had another value, again, and again, and again, you keep doing that. Okay, if you only have two values, you just do it twice. Okay, and then once you've squared those values, you're going to add these squares up, right? And then you're going to take the square root, and that would give you that value there. Okay. Anybody have any questions about that? Okay. That's going to be your absolute uncertainty for that number. What's my time look like? I am past. Okay. Try these out. Next time come, I'll have a question up here, make you do it for it. And you guys can see if you actually can do that. That's the full table, by the way. That has all of them. Talk to me if you're having any trouble reading this table, understanding anything in it. Okay. And we'll see how it does. If you guys have no troubles with it, that's actually the whole chapter we're on.
Okay. So, for the research thing, the literature review, how long should that really
be? There's not like science doesn't really have like a like I probably would expect for yours will be a little longer than like theirs will, because a lot more of your project is like literature review sort of stuff. But I would expect something probably on the order of like 5 really packed pages.
Okay.
And if not packed pages, probably more up into the 10. Okay. But like again, you can get it pretty packed pretty quick.
Yeah.
Yeah, it's very likely you'll end up using some figures and stuff. So
yeah,
like 10 is not actually that much, because one is going to be the references. Then you're going to have to have a figure or two, so that's another page or two.
Yeah. And then so just for the like goals and stuff page, do I wait until wait until we finish, like until we are able to replicate the experiment, then add what, like future goals, are going to start adding?
No, you can start. Yeah.
Because one of my ones, I want to try it on like driftwood, because all the tannins have been pulled out and stuff. See if that changes anything.
That'd be cool. Yeah. No, that'd be awesome. That's a good idea. Yeah, there's all sorts of modifications. In fact, there's also, did you know you can like turn wood clear?
Yeah, I saw that. I didn't read the full article. I just read the abstract real quick, but I saw it was.
We can see how, if those methods could actually mix it all. I have a funny feeling they can't.
Yeah.
Because from what I want to understand of the clear, you actually put a lot of plastic in it. So. But maybe. I have no idea how that would change the strength of it.
Yeah.
Like plastic under certain conditions is just strong as steel. So. Maybe.
Let me see. I might have some more questions. If you have a question, Jasmine.
I have a question. Can you extend the tools of the trade homework? I didn't get to finish it, and I was just want to see if I could finish it. I was almost done with it, but I didn't know if you could extend it, because they like kicked me out while I was working on it, because it cut off like the other night, and I didn't get to finish it. I was just gonna see if you would extend it, like maybe like another day or so.
Have you tried accessing it today?
I haven't, but it kicked me out while I was in the process, and I tried to get back in it that same night, and it still kept me kicked out. Okay. So I didn't know if it was.
I don't know when you did it in the night. Like
I was doing it the night of, because I had worked before.
No. Did you do it later, or did you do it early, or earlier that night?
Later that night.
Okay. Yeah. So probably after I went through, and for some reason the like homework thing where it allows you to do them late decided to not take. Okay. So I would appreciate if you try it out. Okay. And then email me and remind me.
Okay. Thank you.
And I'm I am willing to lengthen that out.
Thank you.
It's like-
I appreciate it. I'll email you if it doesn't work.
Okay.
And
Thank
then
you.
For our meeting, would I be able
Mhm.
to like come to one of your labs and stuff, and then I can just work on like my literature review and finding sources,
You
or
can.
like sit outside and then if I have any questions, ask you.
Yes, but I probably like the Thursday labs and Friday morning lab. In fact, most of my labs, I'm kind of like.
Yeah, I know that, but I mean,
that
I was
might
looking at the
work
stuff
on
for this
Thursday.
week. I was looking
Yeah.
at the stuff for this week, and I really don't think I have many questions. I just really need to start working on the literature review.
Okay. You don't want me to buy you lunch?
I mean,
Man, I thought I would have if I was in college. I
was
really
planning on just going to the CAF.
Yeah.
Because I get that for free since I live on campus.
Oh, you get it completely free?
With my scholarships and stuff, yeah. So it's part of my meal plan.
Oh, well, that's yeah.
I mean, we can talk about it during lunch. I just
no. Yeah, we can do it at lunch, or you can come in on Thursday.
and then
Try to catch me. I probably won't be able to talk to you a lot at the beginning of the lab, but I think what's going to end up happening is I have like an exam coming up, and my labs will probably end a little early.
okay.
So
Yeah.
that might work out. What we can do is if it doesn't work out very well, we can Friday.
Yeah.
We'll do the lunch.
And then what I was thinking, so actually, I don't know how many people you have in your labs now, but I was thinking when I start getting more familiar with the labs, and
20 something.
what is there like open tables and stuff in there or no?
There is, but only because people don't show up sometimes.
Oh, okay, never mind.
Yeah.
Because I'll say maybe when I get more familiar with it, I could work on it while I'm in there, and then
What I'll do is I'm totally fine with that.
Okay.
What you can do is you can work in my office.
okay.
Yeah, I'll just throw you in my office. And
Oh, what I meant is like work on the lab part of it during that period in case, like whenever after I replicate it and I get familiar
Okay.
with that process and we're just adding
that will
modifications.
totally work, but we'll put you in the research in 303.
303.
Yeah.
I don't know which one. Which one's 303?
Organic.
Organic.
Yeah.
Sweet.
So the organic lab, remember there's that bench that never gets used?
Yeah.
And people are always
That's
trying
the
to like
research
put
bench?
stuff on it? Yeah.
Okay.
You can
what I
actually use
figured.
it for what it's supposed to be used for. And it's literally there so you can do research while there's labs.
Okay. And that's the lab I'm gonna do all my research in and stuff.
You got it?
Perfect. Because I was really hoping I got that instead of the other one.
Oh, no. No,
I
you're
did not
definitely
like
doing
the other one.
Because first off, I don't want you breathing all of that.
Yeah. That makes sense.
I would prefer you not having lungs full of that. Yeah. I don't think it's actually that terrible for you, but and it shouldn't be that easy to vaporize. But there's a few things I want to try. Like for example, one of the things I want to try for your literature review thing is I think it can go a lot faster if we do it as sonicator.
Yeah, I saw that on the future goals or whatever.
Yeah, I think we can speed that up a lot, but that will vaporize more of the
Yeah, it'll vaporize.
solid. So
And then
we'll have to be careful.
for the literature review, should I just focus on